taking your phone out of your pocket and going to type in the password, a series of numbers you've typed countless times, and you completely draw a blank. It takes you an uncomfortable amount of time for those numbers to come back to you. This frustrating, somewhat frightening scenario is often a reality for the nearly 3 million individuals in the United States who suffer from a traumatic brain injury every single year. Symptoms like these caused by traumatic brain injury, or TBI, are in part due to one of their more common features, axon damage. As you can see in the image above, the human brain is an incredibly complex network of interweaving natural wiring, all working harmoniously to carry the electrical signals that give rise to our daily lives. Our ability to coordinate our movements, to learn new skills and trades, to process emotion, like how to love, how to cry. And yes, even remembering the passwords to our phones is all the work of our axons. However, axons are incredibly vulnerable to the forces applied to the head during a brain injury. TBI causes them to stretch and twist, to shear and to swell. What you can then imagine is those electrical signals can no longer effectively go from one part of the brain to the other. It's the biological equivalent of me flipping the light switch in this room and the light not coming on for several seconds to minutes, or alarmingly, never coming on at all. The research in our lab is working to figure out exactly how those axons become damaged. Using specialized mouse models and state-of-the-art imaging methods, we're able to see the axons in unprecedented detail, track the progression of their damage over time, and target specific biological factors that may be critical in production of those symptoms. For example, the image on the top right is from a mouse to which we made a very small genetic modification, which in essence causes its brain to glow in the dark, allowing us to see its axons in a detail only dreamt possible just years ago. And as you can see in the computer reconstruction below it, our mouse model bears a striking similarity to that of the human brain. It's genetic engineering like this that allows us to see the incredibly complicated nuances of brain injury that compound to give us disruptive and aggravating cognitive symptoms. Our lab wants to know if a mild head injury affects the brain differently than those repetitive injuries, like the kind we see in athletics all the time, or if a physical hit to the skull damages the brain in a different way than the pressure wave from an explosive blast, like the kind that our military personnel are regularly exposed to. Figuring out the how and the when that our axons become damaged will allow for the development of better diagnostics and more effective therapeutics, so we can hopefully start to help the countless people suffering symptoms from their head injury. Because when it comes to a problem as debilitating and as pervasive as traumatic brain injury, it's our responsibility to make sure when the brain goes to flip on its light switch, the light just comes on.